Hey guys. Okay. Alrighty. So, today we're going to look at a few related rates questions, just to get us a little warmed up. It seems like it may have been a while since you did a related rates question. I thought maybe, just based on the reception from related rates yesterday, I thought maybe it wasn't in your textbook. Because like I said, I'm not super familiar with the first few chapters of this book. From chapter 7, which is when we first started learning together, from chapter 7 on, I feel pretty like I know the textbook pretty well, but chapters 1 to 6, still kind of figuring out what's in it. I looked it up, 4.6, see right here, 4.6 related rates, so it's in there. So that's page 231. So I would imagine that you would have done a little bit of stuff on related rates. In any case, we're going to do a couple examples today. Some of the how would you call it, like the canonical examples, like the classic examples. Ooh, Harvest Crunch, yummy. So yeah, we'll do I think 2 examples that I found that I think are good examples, and they're fairly like well used examples. They're kind of like the examples that a lot of people tend to use with these kinds of things. I had them up earlier and then I closed my tabs for some reason. So let me just quickly find them. So yeah, we'll do some examples on related rates. So today this is kind of what our goal is. So we'll start off with related rates questions. Okay, and we'll do 2 related rates questions. So that's what we'll start off with. And then we'll take a look at Unit 5. Okay, we'll make a list of topics for Unit 5. And Unit 5 is, again, more derivatives. So here we're looking at, I think, what do they call it? Applications of, analytical applications of differentiation. So should be pretty fun. So yeah, this is kind of a bigger unit. Unit 5 has 12 topics in it. So kind of a big unit. But yeah, let's start off with the related rates questions. While I find this, I'm just gonna ask if anyone is having any difficulties with the first few FRQ questions that I've assigned. Are there any issues with it so far, or are we good? Okay, 2 and 3 are good. Okay. Yeah, I just assigned 5 about half an hour ago, I think, maybe 20 minutes ago. So I guess another thing that I can ask is, would it be, I know that one person, as part of the exit slip, a couple days ago I asked about this, and one person suggested that I give you all of the FRQ questions at once. So if you finish one, then you can automatically move to the next one. I have one hesitation about that. I guess the hesitation is, if it was me, I would find it overwhelming, just having all these questions, like, oh man, now I have to do all these questions. Whereas if it's just one question per day, then it kind of just gives you a goal, like, oh, today this is what I'm gonna do. It's gonna take me an hour or something like that. And then it kind of paces you, so it would kind of like automatically pace your work. So what do you guys think? Do you want to just tell me right now what you prefer? Mm-hmm. 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 Yeah, no, I that's kind of what I was thinking. That we'll just do one per day. Um, if Yeah, yeah, because if I gave you five to do on Monday, even though you have the whole week to do it, something tells me that it might feel a little overwhelming. So we'll just stick to one per day. Okay. Yeah. Okay. So I'm glad to hear that because that was my initial idea, and then it was suggested that I give you all of them, and I thought, maybe not, but okay. So I feel validated. Thank you. Okay. So let's do some related rates questions. So just to remind you about related rates, because I am fairly certain that you did some stuff on related rates. In fact, let me just double check that you did do a little bit on it. So okay, okay, okay. Um, aha. Okay. See, I see a worksheet in his because he gave me his folder that has all his assignments and stuff. Looks like he had something on here. Whether or not he gave it to him, I'm not sure. In any case, let's talk about what related rates are, and then let's just do a question or two. Let's do two questions. So it's the in calculus it's called related rates, but I've heard other people call it related rates of change. Okay, and I think that even though it means the same thing, and that's really what a rate is a rate of change. When you say the expression related rates of change, you can kind of see what's going on here. That you'll have like one rate of change, like d, I don't know, let's say dA by dt, and that's going to be related to some other rate, right? Like dB by dt, right? So change typically has some kind of like you're usually taking some kind of derivative with respect to time, right? Because it's a rate of change, and change occurs over time, right? So you'll have two different rates that are closely related to one another. And that's what a related rates question is where you have like two derivatives that work really closely, like where one derivative or like one rate is completely connected to another rate. Okay, so let's take a look at an example, and I'm going to start off with the canonical example, and when I say canonical, I mean like it's in the canon, and I think that a lot of teachers would probably want to slap me on the wrist for talking about canon, because it kind of sort of narrows things down, and maybe you can think of it as like crushing imagination and that kind of thing. But I think that learning about some of the parts of canon, like the canon of math, is important because there's some examples that you just have to see, right? This is just an example that really illustrates related rates very well. It's part of the mathematical canon. And if you don't know what canon is, it's like in like folklore, there's like some canon, like I'm sure that there's a lot of like fan fiction that is like there's Lord of the Rings fan fiction. That's not canon. Like if you have some like if you think that like I don't know, Bilbo Baggins had a special card game that he played, and you like to play that card game, that's not a part of the Lord of the Rings canon, right? Canon is like a part of like the official story. So this is kind of like the official like first example of related rates. So the example is called the falling ladder, okay? And so you've probably heard this if you've done related rates before. So the idea of the falling ladder is that you have this ladder that's leaning up against the wall, and you can probably imagine what's going to happen here. Okay. Yeah, absolutely. Yeah, because physics and math they're very closely related. So so we've got a ladder here. So we've got a ladder, and instead of just like writing the whole question out like word for word, I'm just going to draw a couple of pictures and tell you a few facts. So you've got a ladder leaning up against the wall, and the ladder is just to make the numbers kind of nice is 10 meters. Okay, so it's a really tall ladder. So it's leaning up against the wall like this, and the ladder is it doesn't have any rubber feet on the bottom, so it's sliding, right? It's sliding against the wall, so it's sliding in this direction, and the rate at which it's sliding is 4 meters per second. Okay, so it's sliding across the floor. Now, as it slides, it's still going to be moving down, right? So it's kind of, I guess it's mirrored. My video's mirrored, or no, is it? No, it's not mirrored, but yes, it is mirrored. So it's kind of like sliding down like this, right? So at the top of the ladder, it's like it's not completely clear how fast the ladder is moving in this direction. So the idea of this is that the rate of change of like the up and down rate of change. So if we wanted to call like this length over here h, like the height of the ladder as it's leaning up against the wall, the height of that is going to change, right? So dh by dt, that's what we're solving for. So the idea of this question is saying, okay, if the ladder is 10 meters tall and it's sliding on the ground at a rate of 4 meters per second, okay, the question is, how fast is it falling when the foot, and the foot is like this thing, the foot of the ladder, the feet of the ladder, when the foot, maybe we'll call it feet, when the feet are 6 meters from the wall. Okay, and that's what the question is. Okay, so we don't know exactly what dh by dt is, right? But that's what we want to solve for. Okay, but you can imagine that the rate at which the ladder is falling down, like the rate at which it's going down, is related to the rate at which the feet are sliding in this direction, right? So that, in that sense, that is what we're talking about when we say related rates. We have two rates that are related to one another. Are they the same? I don't know. What do you like? Do you think that they're exactly the same, or like is this just 4 meters per second, right? Like that could be like the first number that you think of. Like, well, if it's sliding on the ground at 4 meters per second, then is it falling down at 4 meters per second? I don't know. So let's think of just a few facts here. Okay. You might be able to see that we have some relationships here with, in terms of like the Pythagorean theorem, right? So the whole thing that these related rates problems work on is usually we need to interpret the situation in terms of some kind of like geometric formula. Okay, so we're going to look for a geometric formula, and we're going to use that formula and throw some calculus at it and see what happens. Okay, so there's kind of like a bit of a strategy, and once we finish talking about how to solve this question, I'll kind of share that strategy with you. Okay, so let's take a look at some of the formulas that we can use here. So let's throw a Pythagorean theorem at this. So the Pythagorean theorem. So I'm gonna call the height of this h, okay, and I'm gonna call the distance here from here to here x, okay. So using the Pythagorean theorem, we have this relationship that x squared plus h squared is equal to 10 squared, okay. Or in other words, x squared plus h squared, h squared, come on, is equal to 100. Okay. Oh, is this 4 meters per second? It's not 4 meters per second. I'm just saying that maybe it is, maybe it's not. It's absolutely not. Yeah, that's what I would think too. So if it was like at that point, like if your x and your h were equal, then the velocities would be equal at that moment. But that's not the time when we're asked about. We're asked about when it's falling at 6 meters, right? So yeah, that's past that point. So would it be going faster or slower than 4 meters per second? I think it's going slower, right? Okay. So does that mean that it was going much faster over here at the top? Okay. I mean, these are things that you can just ask yourself to try to develop a little bit of intuition, right? And you can even try to like imagine it yourself by, I don't know, setting up a similar situation, right? So here's my phone. I don't know if you can actually see this. Can you see this? Probably not, eh? Oh, here, I've got an idea. I've been doing this in some of my other classes, mostly just to take pictures of my cats. But here we go. Oh, look, you can see my mechanical keyboard. This is hand-built, by the way. These are, what kind of switches are they again? They, shoot, I forget what they were called. There's a mix. Most of them are these purple ones. They're not cherry. They're kind of like Cherry MX Clears. But oh, who made them? They're custom made. Clears are like browns except bumpier. Yeah, they're tactile. Okay, I just gotta balance my iPad like this. Okay. Okay, stay. Okay, let's kind of make a mock. And I think you guys can see this, yeah? Oh, maybe better like that. Okay. So just think about the height of this, and I'm gonna do my best to move this at a constant velocity on the bottom. So look at the height, right? So it's not completely clear, like if it's moving super fast. I don't think it's moving very fast here, right? It looks like it's almost staying the same. So it's like it's very slow at the top, and it's also like I don't know, it looks like it's pretty fast at the bottom, right? Like I don't have to move it, like I almost don't have to move it at all over here in order to, like, it doesn't move almost at all at the bottom, but it moves a lot in height over here, right? So interesting relationship. Anyway, oh shoot. Oh, and I opened up Microsoft Teams by accident. Okay. Oh, yikes. I know. Okay, enough of that. Okay, we're back to normal, right? Okay, here we are. So let's attack this with algebra. Okay, so there's a few things that we do know. So this rate of change here, like this rate of change we know, right? This is 4 meters per second. But what is 4 meters per second? Like in using calculus terms, which variable is 4 meters per second? Is it x? Is x equal to 4? No, what is dx by dt? That's what's equal to 4. Yeah. Exactly. So that's equal to 4. Right? Right, perfect. So that's equal to 4. We're looking for dh by t. So this is what we want. We have this. So we have this. Let me just kind of organize some of our information here. So we have this. We want dh by dt. Okay, so this is what we're looking for. We also have one other thing. We have that in this case x is going to be equal to 6. So x in this case is equal to 6. Now we have to be a little bit careful. We can't just all of a sudden turn this into a constant. X is still a variable, but what we're going to do is we're going to take the derivative with respect to time here. We're going to take the derivative with respect to time, and when we do that, we'll get a new function that has x and h in it, and we're just going to plug in whatever x is equal to at the end. So just because x is equal to 6 doesn't mean that your first step is to replace all the x's with 6. That's like your last step. So we're going to evaluate our new function at x equals 6. Okay? Okie dokie. So let's start by solving for h. Okay, because that's kind of the focus of this equation here, because we're really most concerned about h. So I know that h is equal to the square root of 100 minus x squared, right? So if I were to take the derivative of both sides, let's go ahead and try that out. So let's do dh by dt. So we'll take the derivative of both sides. So d by dt of this square root. It's not that bad, minus x squared. So one thing to keep in mind is that dh by dt that's totally fine to calculate, right? Because that's what we want. We're going to leave that as is. One of the problems that we're going to have is that x is a function of time, right? X is a function of time. So we don't get to just like let's say that we had d by dt of x squared. That's going to be, well, we'll have 2x, but then we have to write dx by dt, right, using the chain rule, because x is a function of time. So we can't just say like, okay, like d by dx, d dx of x squared, that's going to be 2x, right? But because we're not differentiating with respect to this variable, we have to understand that this variable is a function of time. So using the chain rule, we have to throw in this dx by dt, which is good because we have this information, right? We're going to have to use this at some point. So it is good to see that we'll have a dx by dt. So I'm going to erase kind of some of this stuff so I can have a little more room. Yada, yada, yada. There we go. Okay, so does someone want to do that for me? I don't really feel like taking that derivative. I mean, it's not too bad. Pardon me? Yeah, absolutely. Yeah, you could do implicit differentiation here. That would actually probably be much easier to do. But let's just carry on with this thought and finish it off in this sense. So we're going to take, right, so basically what we're doing is, yeah, I'm gonna go ahead and just write this. So I'm gonna take d by dx times dx by dt of yada yada yada. This is 100 minus x squared to the power of 1/2, right? And then I'm going to move this dx by dt on to the right over here just to get it out of the way. And then we can kind of see where this dx by dt is coming from, right? So, so this is going to be what? 1/2 of 100 minus x squared to the negative 1/2 times the derivative of the inside, which is negative 2x. Yes, I think that's right. And then this 2 is going to cancel with the half, right? So I'm going to get something that looks like this. This is equal to negative x over the square root of 100 minus x squared. And I forgot the dx dt. Okay? And all of this is dh by dt, right? Let's not forget about that. So yeah, so d by dt is equal to d by dx over dx by dt. Because they work just like fractions, right? We can cancel those out. Just don't cancel your d's because it doesn't work like that. So yeah, that's kind of the gist of it, is that we're using the chain rule to attack this problem. Now, let's see here. So dh by dt, which is what we're looking for, is equal to negative x over the square root of 100 minus x squared times dx by dt. Now that we've solved this, I know what x is, and I know what dx by dt is, right? I'm told that in the question. So dx by dt is 4, so I'm going to turn this into 4. And x is, what did I say x was? 6? Yeah, x is, in this case, 6. So let's turn that into a 6 and another 6. And now it's just arithmetic. So dh by dt is equal to negative 6, or let's do negative 24 over the square root of 100 minus 36 is 64, right? It's almost like someone thought of nice numbers to give us. So dh by dt is equal to, what is it, negative 3? Great. So let's interpret that. Let's see if that's consistent with our intuition. Well, first of all, it's a negative, right? It's a negative, which is consistent with the fact that it's going down, right? This is going down. That's perfect. That's what that, I mean, if it was positive, we'd have an issue. Yeah, go ahead. Because that's what dx by dt is. Dx by dt is 4, right? Dx by dt is the rate that the ladder is changing, right? Because x is the position of the ladder. So dx by dt is the rate at which it's moving, which we're told is 4. So that's where that 4 comes from. Yeah. So anyway, yeah. So the fact that it's moving down means that sorry, the fact that it's negative means that it's moving down, which is consistent. And 3. Well, let's think about what our units would be. I mean, I've kind of been ignoring the units. If I was a really good teacher, I'd include the units at every step. But I kind of like to ignore the units and then just throw them in at the end. But yeah, I mean, thinking about your units is important. I just didn't really feel like it. So yeah, we've got negative 3 meters per second, and that is a little bit slower than 4 meters per second. So that, again, that is consistent with our intuition that like at the top, right? When the ladder is moving just a little bit, it doesn't really move much at the top, so it's really slow. And then at the bottom, it's like really fast. It would probably be faster than 4 meters per second. And when it's at 45 degrees, it would be kind of exactly the same speed, right? So it seems like it's past that 45, which maybe that contradicts our I'd have to think about that for a little bit. Mm-hmm. When h equals w, sorry, what's w? Oh, okay. Okay. Oh, yeah. Height and width. Sure. Yeah. Mm-hmm. Mm-hmm. Right. Yeah. Yeah, I'll think about that. It's hard to think of that on the spot. For some reason, it made sense in my head. Um, but in any case, like our algebra checks out. It's -3. So that's how we would solve it. So the gist of these problems, the way these problems work, is that like our strategy. Oh, do you have an idea? 6 is smaller than 8. Oh, yeah, because we're not at 45 degrees yet. Oh, yeah, okay. Yeah, there you go. There you go. Perfect. So it is consistent with our intuition. Perfect. Perfect. Okay, anyways, our strategy for these kinds of problems is the following. So we're gonna, like, you just have to do this, and especially so on the exam, and this goes for all of the problems that we're going to be doing, is to list all variables that we know, right? You may have to assign your own variables, right? So you might have to have like an x, tell me what like d by dt is, like dx by dt. You just list everything that you know. Okay, so that's the first part of your strategy. The second part is to find a formula that describes the situation. And it's almost always a geometric formula. That's kind of how these questions work. Is that it's kind of like a real world situation. So you'll have to know quite a few formulas. Like formula for like the volume of a cone, Pythagorean's theorem, or the Pythagorean theorem. You definitely need to know that. Just being from. Go ahead. Yes, exactly. You may have to rotate something around a washer or something to get a geometric formula. No, hopefully the formulas would be fairly straightforward. I'm going to do one more example. We may go a little over time today, but I think it's important that we do this example too. So yeah, find a geometric formula that describes the situation, and then the third step is to take a derivative, or actually I shouldn't say take a derivative, I should say differentiate with the intention of, I'll say, revealing all rates in the question. And in these questions, chain rule is like 99% of the time you need to use the chain rule. Okay, so if you're not using the chain rule on one of these types of questions, you're probably making a mistake. So make sure that you're using the chain rule here. And that's pretty much it. So you list all your variables, find a formula that has all those variables and kind of describes what's going on. And then we're going to differentiate with the intention of revealing all of those rates, so all of like the dy dt and dx dt, and pretty much all these questions also are dealing with rates of change, which of course is like d variable by dt, right? Like what I'm trying to say is that we're differentiating with respect to time. Okay, so almost all of these are differentiating with respect to time. I'm gonna steal one of Sal Khan's examples here from Khan Academy. This is a great example. Again, kind of part of the mathematical canon of related rates. So yeah, let's take a look at this one. So let's say we have some kind of cone. Okay, and if you just look up Khan Academy's video on related rates, this one's called Related Rates, Water Pouring into a Cone, and it's AP Calculus AB. He explains it. He'll probably explain it in much greater detail than I'm going to because I want to wrap this up. So you can look that up if you want. So let's say that we've got this conical sort of like water basin or something that's collecting water, and it's slowly filling up with water, right? So this is our water. It's being poured into our cone, and let's say that we have some kind of tube like this, all right, and water is flowing from the tube into our cone. And why the water's going from blue to green beats me. So here, now it's blue water. Perfect. Okay, so there's our cone, and the question is, if the rate of the water, so the rate of the water is 1 cubic centimeter, 1 cubic centimeter per second. Okay, so that's the rate of change of the water. So that's the rate at which the volume of water is changing with respect to time. Okay. Once the height of this water, when the height of the water is, 2 meters, I think? Yeah, or 2 centimeters. 2 centimeters. Yeah, it would be kind of mean if it was 2 meters, because then you'd have to change your variable. In any case, when the height is 2 centimeters, what is the rate? What is the rate of change in the water level? And the water level, of course, is H, right? So the water level is like, where is the water on this cone? So when the water level is at 2 centimeters, at what rate is the water level changing? Okay, so that's what we're being asked. So there's a few things that we need to be aware of. The first and most important thing is, what are we looking for? Like, what are the variables that we want? Well, we want the rate of change in the water level. So that would be dH by dt. Okay, so this is what we want. Okay, this is what we have. We have that the volume, the rate of change in the volume, so dV by dt is equal to 1. Okay, and we also have that, H is equal to 2. But remember, this value right here, this is what we're going to evaluate our derivative after the fact. So after we differentiate. Like it's a very, pardon me? Oh, that's a good question. We'll probably need to find the radius at some point. That's a good point. Oh, yes. Yeah, that is a very good point. I forgot that's one other part of the question that I forgot to include, the dimensions of the actual cone. Because the solution would be much different if your cone looked like this, right? It'd be much different if your cone looked like that. So part of this is that the height of the overall cone, the height is 4 centimeters, and the diameter of the entire cone is also 4 centimeters. Okay, so that means that if you took like any sort of section of this cone, here let me use a different color so you can really see what's going on. Let's do purple. So if I took any other section of this cone, then the height would be equal to its diameter. Okay, so at any point, the water level, the height of the water level, like this h is also going to be this h right over here. Okay, so these are the same. Okay. Yeah, that's a super important fact that I forgot to point out. Okay, so we have these facts. So one of the formulas that we're going to want, the formula in this case is the volume of a cone. Okay, and it may have been a while since you've done this, but the volume is 1/3 pi r squared times height. Okay, so and if you forget how to calculate that, any kind of pyramid type of shape, like a pyramid, like a square pyramid or a triangular pyramid, or even like a hexagonal pyramid, whatever that looks like, the volume of these is always going to be 1/3 times the area of the base. Actually, we usually call that b. 1/3 times the base times the height. Okay, and the base is just the area of that bottom part. So this would be b right there, and then the height is just the height of the entire thing, and then 1/3 is obviously just 1/3. So that works for all types of cones and pyramids. So it works for cones as well. So pi r squared, that is the base of this. So basically like the face of the circle here, right? And that's the 1/3 obviously, and height is the height that we're looking for. So the thing is that we don't actually have r here, but since the diameter is equal to h, the radius is equal to 1/2 of h. Okay, so we can replace this with v is equal to 1/3 times pi times h over 2 squared times h. So let's clean this up a little bit so our formula is easy to work with. So it's 1/3 times pi times h squared over 4, and we can clean that up even more. So v is equal to 1/12 times pi. Actually, let's make that pi over 12, just so that our constants are all together. We got pi over 12 times h squared. Okay, so this is the formula that we're going to use. So that's the connection between v and h. Now we need to find, go ahead. H cubed, thank you. Yeah, h cubed. I forgot for the other h. H cubed, and this should be h cubed as well, because h squared times h is h cubed. Yeah, so that's the connection between v and h. Now we want to find the... Why did I circle this? Like this thing here? Because I was making the connection between these formulas and this formula. So b here, this is the base, which is the face of the cone, which is a circle, and that circle has dimensions pi times r squared. We don't really know what r is, but we know what that the diameter from here to here is the same as the height, right? Because in the big cone, the height of the big cone is 4 centimeters and its diameter is also 4 centimeters. So the diameter is equal to the height for all of the cones. So that's where this formula comes from. Does that answer your question? I haven't taken any derivatives yet. Pi. Yeah, so the diameter, can you see that the diameter is going to be the same as the height? Right? This is the diameter, this is the height. And because all of these are going to be like similar triangles, we're going to have that for all of these, the diameter here is the same thing as the height. Okay? So the diameter is equal to height, then the radius is 1/2 of the height. Right? So the volume of a cone is 1/3 times pi r squared, because pi r squared is the base, right? Yeah, you see it now, times height. And then r, I'm just trying to simplify everything until we just have one variable. R is equal to 1/2 h, or h over 2, right? And then the rest is just algebra. So the connection between v and h is here. Now we want to find the connection between dh dt and dv by dt. So we're going to differentiate both sides with respect to t. So let's just start a new slide here. So I've got d by dt of v, and I'm going to put everything in brackets, and d by dt of everything else. So pi over 12 times h cubed. Okay. Now, on the left-hand side, we're pretty much done, right? We've got dv by dt, and this is something that we know. So we don't have to worry about like using the chain rule or anything like that. This is a variable that we have, right? It's right here. dv by dt is 1, okay? So that side is done. The problem here is that we're differentiating with respect to time, but h is not time. However, h is a function of time, right? Therefore, chain rule. Okay? In other words, d by dt is the same thing as dh by dt. No, that's not what I wanted. D by dh. Yes, d by dh times dh by dt. Okay? So, in other words, you could cancel these out and you get d by dt. So, we are going to do all of this. We're going to take this derivative, but we're going to have to sort of move these terms around a little bit just so it looks nice. So this is going to be equal to dh. I'll put the dh by dt out front, okay, because we know that this is what we want. Like, this is the variable that we want, right? We want to know the rate at which the height is changing, right? This is the thing that we want, dh by dt. So there it is. And now we're going to solve d by dh of pi over 12 times h cubed. Okay, and we go back to purple. There we go. Okay, so almost there. I know I've gone over time, but live with it. So we've got dh by dt times, well, now I just take this derivative. This is going to be pi over 12 times 3h squared, right? Or in other words, let's just turn this into pi over 4. Okay, and I'll move this over here. There we go. And we're pretty much done now. So the equation that we get, so let's kind of move this back down. This is dv by dt. Well, dv by dt is equal to 1. So 1 is equal to dh by dt times pi over 4 times h squared. And h, we said after we differentiated it, h is equal to 2, right? Because we want to know what the rate of change is when h is equal to 2. So let's turn this into 2. So this will be 2 squared, which is 4. And 4 over 4 is just nothing. So dh by dt is equal to 1 over pi. Okay, and there you have it. That's the solution. So if you want kind of a further, like a more detailed explanation of all the different steps, you can look at Khan Academy's video. I pretty much just copied the whole question, almost pretty much word for word, but his solution might be a little bit different than mine, or not so much the solution, but like his methodology, maybe a little different than mine. So I copied the question, but I didn't copy his solution. So you could look at his video. He might explain it in a slightly different way than I did. I think that what he did was he did something like he turned this into h of t cubed, and I didn't quite like that. But maybe you prefer looking at it that way. In any case, you could look at his video and see what he did, and maybe it would make more sense. In any case, the methodology remains the same, right? The first thing we want to do is list all our variables. Oops. We want to list all our variables. Then you want to find a formula that kind of connects some of those variables, and then differentiate with the intention of revealing those like dh by dt and dv by dt, so that you can get those related rates in the equation, and then you can start solving for them. And chain rule is your friend here. So I guess as for the exit slip, I'll make it simple. The exit slip for today, I'll just say what was the solution to the first question. Okay, the first question that we did today. So what was the solution to the first one? The one with the ladder. So so you can just refer back to that. Yeah. Okay. So you guys have some work to do. I guess we didn't quite get to the listing of the units, which I said we would do, but we already went over time. I posted a little package on our website. So on our website, if you go to AP Calc, right on top of yesterday's video, I guess that would be April 30th's video, I put a button, and the button says, I guess I can just show you. Yeah, exam package, I think is what I called it. So if you go here, AP Calc, AP exam package. So that'll just open up a Google Drive link, and yeah, here it is. And it's got a few things. It's got a couple URLs as well. Those are the ones that Ron shared with us. Also this PDF Ron shared with us. I would highly recommend going through this. I guess I can't preview it here. I'm using Microsoft Edge, which is not the best browser. Anyway, yeah, so you can kind of mull through this. The list of topics, I've kind of got it twice here. So I guess you can't really see where I'm pointing here. So this is basically the whole course. So this is a very thorough document. It's like quite a few pages. For kind of a more concise one, I just put here in units. These are all the different units. So if you want, you can go into Unit 5 and just scroll down, and it'll tell you all the different topics. We are BC. We're BC. Yeah, we have all the units. But there's almost no difference between AP and AB this year. The only difference is sequences and series. There is an AB. Oh yeah. Okay. Yeah, the only difference between AB and BC this year is the inclusion of sequences and series. Usually there's two two chapters, or I guess 2 units that aren't on A, B, which are sequences in series and polar coordinates. But since they're not even including polar coordinates, the only difference is sequences in series. So almost exactly the same over here. So you can even see here, the purple ones at the end are BC only, and Unit 9 they're not even doing. So the only difference is that there's some sequences in series. But if it's 2 questions, like I don't know how they could do all of these topics with 2 questions. So yeah. Yeah. Wouldn't that be nice? Yeah. So yeah, definitely take some time to read over this. The one topic that I would recommend reading the most, like if you're only gonna read one thing, read this, which is the. Let me just steal my mouse. Here we go. Read this thing right here. This is extremely important. This is the testing guide. So this is going to tell you everything you need to know about what the test is going to look like in terms of which web browsers are supported, if you can use your phone. It'll tell you a little bit about uploading stuff and a practice test and everything like that. And then these 2 links are little practice tests, but you do need like I think it's called a student token. We sort of talked about this a little bit in yesterday's class, but I'm not really sure what that token is all about. I assume that'll be emailed to you at some point. But if maybe we can start exploring these in a little more detail next week. Anyway, I really have to prepare for my next class. I'm gonna go. I gotta steal my mouse back so I can exit. But yeah, if you have any questions over the weekend, don't hesitate to reach out. I know that our Unit 5 assignment is due on Monday. We do not have class on Monday. Did I tell you that already? Yeah, okay. It's a in-service. So I'll still be around. So if you want to chat, like if you're curious about one of the questions, don't hesitate to reach out. But we will not be having a class. So I guess I'll talk to you guys on Tuesday, and have a good weekend. Bye-bye. And goodbye, YouTube. Take care.